Ethan, are we ready? Are you ready? Okay. Okay, so this is week 5, and we're doing the part 2 of insulation. And we talked about all different kind of insulation, the relationship between density and R value. And what is R value related to?
The U value.
Yeah, what?
You're saying what it's related to?
Yeah.
The R related to the U value?
Well, the U value depends on the R value. The R value depends on the thermal conductivity of the material and the thickness. So you might go and buy some material and it has a K value and it has thickness. So you find the R value using the thickness and the R value. We talked about all different kinds. I would say there's cavities in the insulation, and those cavities do make a difference in holding the air, because air is a good insulator if you can keep it in place. That's why you always, when you try to cool things, you blow on them to remove the air, because the air as it's still, it's not really good conductor, but it does move a lot. So fiberglass pads blown or board, this is per inch. You see the resistance per inch, 2.6 to 4.2. So the resistance, you want a high number. The U factor, Dave, the U factor is because it's the reciprocal, it has to be lower. And because, again, this is our heat loss. So the lower the U factor, the lower the heat transfer. And the higher the resistance, the lower the heat transfer. Because again, U equals 1 over R. So it's the inverse. Cellulose bone, we said this is all newspapers that are treated for fire retardant and water resistance. They're very inexpensive. Mineral wool bats, blown or board. This word that I cannot say.
Vermiculite?
I'll try that. Vermiculite or perlites, those are particles that are blown like popcorns. It's some kind of rock or material that you heat up and it just pops up. And the idea is, when things pops up, they're absorbing gas and they have gas trapped in them. That's why you say the kernel of a small popcorn, it gets bigger because it's absorbing a lot of gases and it blows up. So they have really good R value. Polystyrene, different colors. There's white, there's blue and pink, and we saw those as boards. They're very common. So these are they have good insulation, lightweight, easy to work with. You can work with them with exact knife. And this is the white one, polystyrene. And there's also polyethylene, which is different kind of material. They all do the same. What is this is around 4 or 6. This is 4. And again, there are other ones. And the prices of these goes per thickness. The thinner and more insulation, the more expensive this will be. So you want it to be thin because that's easier to work with and it's easier to install. So the most expensive one I saw for scientific equipment, it's around 1 millimeter and it has an R value I think of 20, and it's around $100 a yard. But that's when you don't have a lot of space and you want to do some insulation. They're very good for cars as well, because you're going to put some insulation on the roof. You don't have a lot of space, you can't put stuff that's in there. So you want something very thin and with a very high insulation. Question?
Wait, so if you use spray foam that has RA, and you're filling in a 2x4 and you only use half of it, and then another one you use you fill the full 2x4, would it still be considered R8, even though you only use half?
If you read the can, that will tell you R8 per thickness, how much you fill.
Oh,
so there has to be a function of thickness.
Also, it depends on how thick it is. That's the R value.
Yes.
Okay.
show you the aerogel. It's pretty cool. It's it comes into blocks. You can spread it. You can fill material with it. But this is how insulating it is. See how thin it is? And it comes also as as sheets. These are the sheets. Aerogel. So if you have a project and you want to splurge on it and you have a small area and you want to install it very well, you can put that in it. This is the fabric. It's very thin. Again, it's very expensive, but I think this fabric, the last time I checked, it was $100 a yard. But if you put this in an oven, it's not a bad price, you know. If you have an oven in a restaurant and you want to insulate the oven to save money, that's not a bad investment. And probably you'll see it in some really industrial ovens. That's why they're expensive. So yeah, this is the best insulation so far. And the research is going. It's ongoing.
Completely fireproof?
Yeah. Again, to an extent, it has limits to how hot it is. Water and insulation. If you get water inside your insulation, that's not a good thing because you are again filling the gap that you count on for insulating the material. So you don't want water to get to insulation; it will fill it up. I mean, for this, it's kind of waterproof, and sometimes, but it has the ability to grow stuff in it. It might not deteriorate the insulating value, but it's not a good surface to resist water. Some polyethylene, they have aluminum foil. On top of that aluminum, they have Teflon layer, so it will not be sticky and water will not stay on it to deteriorate the material. Water and ice, if you have moisture accumulating inside inside your insulation, that's also going to be an issue for ice. You're gonna have ice and ice dams in places where you don't want it. Corrosion is another issue. You might corrode the nails that's holding your wood together. You might corrode your pillars, you corrode some support. So again, you wanna have the proper insulation and think of the water and moisture coming into the house. You want something that will deter that. There's also something called craft paper, if you've ever heard of it. They use that in insulation, which looks like a baking sheet, has wax in it. But the idea is to have some kind of moisture barrier. Bacteria is another issue that happens if you have moisture, and some bacteria are strong enough that will eat wood and will eat all your construction material. Anybody hear about wood rot? Yeah. If you have rotting in your basement and you're not aware of it, you have to replace the entire wood, and it's very contagious. It will eat the wood. By termites, the wood is rotted, so it loses its ability to be strong, and that's why a lot of wood used for construction is treated. They treat the wood, they soak it in some kind of chemical, so it bless you, so it will not absorb water and eventually it will not grow bacteria and rot. Yeah. So that's something you have to think about because bacteria is not just something that's unpleasant; it's can eat your building material. And everything can deteriorate.
That's why all the houses are deteriorating.
If it's not well built, yes. If you don't build it right, it's not very well ventilated, something gonna come and feed in that material. Whether it's metal, aluminum, insulation, there's always something that will come and eat at it. Thermal mass and thermal inertia. That is a very good concept that I want to talk about, and I just want to have you think about it. So when we talk about thermal mass and thermal inertia, what comes to mind? What has more thermal mass? What do you think of? So, huh? Think of objects. Think of ovens. Think of bricks. Think of building material. So thermal mass is how much a mass can hold heat. Like water has really good thermal mass, right? If you heat water, it will take a while for it to cool off. So material has the same properties. Different material have different thermal mass based on their size and based on their composition. So thermal inertia is how fast do you give off that heat. If you have a big block of steel, you heat that steel. it holds a lot of temperature. But how long will it keep it for? Not too long. Once you start heating, it will go off quickly. What are most ovens made of? Like pizza ovens, like old-fashioned ovens, clay ovens, bricks. Why? They have good thermal mass. Yeah, it does too. But and that's because of the thermal mass. Why? So if you go to authentic pizza ovens, what do with when they use the charcoal? First, the guy comes at 4 in the morning, and they fire the oven. They put a lot of wood in it. They fire it and they close it. They keep it firing. When they're ready to bake the pizza, they put the fire aside, and they cook using the thermal inertia of the oven because it's more uniform. And that's why it tastes better. That's why it's crispy. That's why it's not like burnt from one side to another. That's why if you're into cooking, you buy pizza stone. So it will give off heat in a uniform manner and cook it evenly. So that's thermal mass. That's why cooking with copper or thick pot is different. Does anybody cook here at all? Yeah. So if you cook with a very thick pan, it's different. So you heat it up, the uniformity of the temperature matters and how fast does it give off the temperature in and out. So that's what we talk about, thermal mass, how much you can store, and thermal inertia, which is how much what is the duration when you give up the temperature. The low grade pots, usually like a very thin, made out of stainless steel, aluminum, which give off heat quickly back and forth, which is good for some type of cooking. If you want to do some kind of sauteing or something, you need a lot of fast thermal inertia. It has a number between 1 and 2.6. You don't have to remember that. And it increases the R value. So brick will take a lot of time to heat up, which means it has a lot of resistance, but the heat's not going to go through it very fast. What's up?
It's fucking laughing at me.
Yeah.
Why?
What was the dance you were doing?
Oh, I'm anxious.
Okay.
My fault. I wasn't dancing, I had to stay moving. Alright,
Okay. So outside insulation have a mass factor of 2.6, and inside insulation have the mass of 1.4. Now I had that theory stuck in my head. Okay. So why do we do mass inertia and mass thermal mass? Is because when you build, you want to think about you gotta think about building material. Why you want surfaces that are exposed to the sun to absorb the heat and release it during the night. In California now, I did say that before, that they have bricks filled with wax. So the wax has a lot of thermal inertia. You heat the wax slowly. As it cools off, it will give off heat. This is a very good concept. Please think about it. They have a lot of something called passive cooling and passive heating. What it does is the material selection plays a big role into absorbing the heat and keeping it. So you do not have to put a lot of heating and cooling. And please look into it tomorrow. I'm going to a conference. You're more than welcome to come. It's in, I think, near Worcester. It's Mass Green Career. I'll bring any flyers and any new things. And I love to go there because you see a lot of startups and a lot of companies that actually do a lot of new age stuff. Like houses that do not require heating and cooling. Houses made out of mud and hay. Houses that facing the right direction. So that's really important. And it's getting a lot of momentum now, having like passive cooling and heating, and you will hear those terms when it comes to insulation. So think about that. What is insulation made of? Minerals. What are minerals? When we say minerals, huh?
Stuff.
Well, example. Salts.
Glass.
Salts are minerals. Matters that trap air. So we have fibers, and we want insulation to trap air. We don't want it to be permeable. You don't want air to pass through. You want to trap air. You can make it also out of plastics, because plastics have very poor thermal conductivity and has the ability to trap air. Glass fiber, fiberglass, and again we're doing the same thing. Or cellulose, which is tree fibers that made out of wood and eventually became into papers, and it holds temperature. So if you look at what you're wearing right now, flannel. Why flannel is wool? It's fibers, right? It's fibers, it trap air. If you put it against a fan or something, air is not gonna go through it. So flannel is very comfortable. What the Dan is wearing now is like a windbreaker. Again, it traps air, it prevents air from going in and out. So think about how air passes through it and the type of material that actually we consider as insulating material.
That's why you see roofers on 110 degrees on a roof and they're wearing long sleeve
Yeah.
pants and the
Yeah.
same situation.
Yeah. So we think of the materials we use for insulation. Wall installations are also called bats. Usually, it's better for these things to be installed before you put in your drywall. Because as you can see, they come in very packed formation. So you put them together and make sure it's stable and there's no air going through it. And the problem is after you put your drywall, it's really difficult to put these in. So you're gonna have to rely on blown insulation, cellulose, which is not that effective. Some of them are really covered with foil sheets, which is good for thermal barrier, moisture barrier, air movement, and also what foil is good for radiation. So it will reflect whatever heat that is passing through. And usually they are non-combustible material. So a lot of things has been sprayed with fire retardants. What is fire retardant made of? So no, I think some other chemicals, but there's a lot of now new regulations that are against using fire retardants because that have been affecting a lot of the wildlife and plants around us, because eventually they wash out with water, so they don't really stay that much, and then it's water resistance. So as you wash it out, it will go to the drainage and eventually it will accumulate, and it's affecting a lot of the fishery and marine life. So density, I want to ask question. So we talked about foam, and we said density is very important, and all insulation has something to do with density. What is density?
How closely packed the molecules are.
Okay, is weight per volume. So if you have 1 pound of cotton and 1 pound of steel, which one is heavier?
Just looking very close.
So, but which has more volume? The cotton, right? So it's volume per weight. If you have very dense weight, you have this material, it has more weight. It has the same weight, but it has like less volume. So high volume and low volume. So this 3 times volume, and volume is depth, width, and height over conversion of feet. So again, we also have this issue with feet and inches. I don't know why we always have to divide by 12, but anyways, in the metric system there's centimeters and meters. Now we have inches and feet. So when you measure wall cavity, you're not gonna go with foot, right? You're gonna go with inches. But at the end, you have to convert inches into feet. So it's very confusing. But again, notice inches, 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 and feet cubed. We need to know that. Why? Because we want to achieve the right density of the insulation. Otherwise, it's not going to serve the purpose. So multiply the density of the insulation that you want to use of the wall, and you'll get the weight. Why? Because if you go to Home Depot, if you go to any warehouse store and you want to buy insulation, they sell you insulation, loose insulation per weight, a bag of 20 pounds. So you want to know what is, the bag probably will say that for best insulation, achieve such and such density. So you have to put the insulation, have it packed, and make sure you get the proper amount of weight inside the wall. Does anybody understand what I tried to explain? No. So you have a cavity in the wall. Sorry if I went through it very fast. So let's imagine this is a wall, okay? And it's empty. and I want to fill it with insulation. I want to know how much weight of insulation should I put there to achieve the proper density. So I'm going to use, for example, cellulose, and density is supposed to be 3 pounds per. Let's see, density is incident volume, so 3 pounds per foot square, 1 foot square. So to tell you, for example, this, you buy a bag of insulation, it will show on it. This is the density of the insulation that should be in to get this R value. Because what Connor was saying before, if I have a spray can for insulation, it says R8, I have to know R8, how much thickness per inch. So I have to calculate this volume. So I'll calculate this volume here. Volume equals depth times, which is the depth here, height, and width. I get the volume, and I get the density of the insulation. I have to find how much weight do I put inside the wall. So you're gonna go and buy the insulation per pound, 20 pounds bag, and you find how much weight is required. And you find, for example, it's 10 pounds for this cavity. You buy 10 pounds and you stuff it in there. Because if you buy 5 pounds, and because when you blow it in, when you put it in, it's gonna be loose. So you might have to want to know to put it there. And if you pack it too much and there's void, you fluff it back again. For blown in cellulose, usually they do the blowing in. Somebody will come and blow it in, but they have to come back later and blow it again because it settles. So always be careful with that.
Don't they also have to cut the excess off that extends outside of it?
Yeah. So this is density and weight. For example, we have a wall 3.5 inch deep, 14.5 inch in width, and 93 inches in height. The cellulose density is 3.6 pounds per cubic feet. How much do I have to pay to buy to fill in that cavity? So that's why we need to know the weight. And that's why you have to double check if somebody's doing insulation, that they know what they're doing. So I'll work on this example. This is my wall, and I have 3.5, 14.5, and the height here is 93 inches. So volume, I notice the units, inches, so I have to divide by conversion. That's inches cube. So to convert from inches cube to foot cube, we're going to divide 4719.75 by, what is the number?
3.6.
No. Converted number. 1728. Which is supposed to be 12 times 12 times 12. You know what that number is? 12 times 12 times 12.
2.73.
Where'd the 12 come from?
Inches per foot.
What's 12 inches?
We're trying to find the volume in feet cube, and we have the measurement in inches. Because usually when you measure walls, it's in inches.
12 inches.
Yeah. So if you convert in the beginning, you're all set. So this is basically a conversion of all these inches. And we get 47.9.01 over 17.28. That 2.7.
Okay, but where'd you get the 1728?
This is 12 times 12 times 12.
Oh.
Because over here, to convert that into feet, you're going to divide by 12.
So it's literally 12.
So this was 12 here, over 12 here, over 12 here. You can convert first, then move on to
That
the
way is a lot easier if you say it like that.
Yeah.
12 times 12 times 12.
Yeah.
Wow, really good frustration.
Whichever way is easier for you. So how many pounds? So for the weight here,
2.7.
weight equals density times volume. What is the density?
Depth times width times height. Density times volume.
Volume, which is 2.7.
So you divide the 3.6 times.
Multiply. So I get around 9 pounds.
Yep, 9.72.
Okay? Anybody confused? We'll talk after class. Huh?
Are we gonna do this again like tomorrow?
Okay, well, I'll explain it one more time. Because this is important because you don't want to be putting the wrong volume in the wall and not getting the proper insulation.
I'm just confused as to what you do after you guys volume.
Let's backtrack a little. Let's say this wall over here. We decided it's really bad, has bad insulation. Okay? It has a volume inside, you agree? It's hollow. I want to fill it up with insulation.
Yeah, I just need to know what you did after you got the volume. That's all I need to know.
Yeah. So after we get the volume, the weight equals density times volume.
So that 4,000 number, what'd you do with that 4,000?
That was the volume in inches cubed.
Okay.
I converted that into feet cubed. Because when you buy insulation, it's going to be, it will give you a density in feet cubed. So I'm just converting from inches to feet.
Okay.
To do that, I'll divide by 1728, which is conversion of each one of the little units from inches to feet. Every foot has 12 inches. And that's how I got a volume of 2.7 feet cubed. Everybody with me here?
Okay, but why'd you put 3.6 pounds over?
That's what it says.
The density is 3.6 pounds.
Yeah, this is
Over the.
this is the density.
Yeah, so you put the pounds over the feet.
This is the unit.
Yeah,
This is the unit of density.
that's just the unit.
Yeah. And if you multiply this by this,
Your
This
answer
will
times
cancel
the
out?
density.
and you end up with pounds. If you're confused, raise your hand. It's gonna be, there'll be a quiz question about it. Okay. So we agreed that yeah.
Should be on this Friday's quiz?
No. You want it to be?
Hell no.
Yes.
You hear this? Okay. So density is given by pound per foot cube. You're gonna find density any insulation cube by pound per cube. So you want the volume to be in foot cube. If you put the volume in inches cube, it's not going to be the same answer because it's a different number. Okay? So first you find the volume, and you read the density. This is supposed to be given. This is how you get the weight. the insulation. Unless you have to be careful with the consistency. If they give you the density per inch cube, keep it not just compare it, use online, use Google, but make sure that units are consistent. When I multiply those numbers together, whatever I got from here and here, I should be getting only pounds. Okay?
And all the numbers are up
Huh?
there. All the numbers are up there.
Yeah. So, think about it a little bit and, how many pounds? Huh?
Yeah.
Do you know what pound is, LP? LP? Oh, ouch. It bothered me like seriously, I had to go look it up. Apparently pound is libera in Latin. Okay. We're good with this?
Fantastic.
Alright. Other types of insulation. So we have rigid fibrous insulation that is used to insulate masonry walls. If you have brick wall or stone walls, you can use rigid fibrous insulation, which looks like a board. It can also be used with steel and wood building components, guys. So if you have a hollow door, probably can put rigid fibers in it, kind of like sheets. And again, if you're trying to put panels, make sure they are connected together. Do not leave a lot of holes and gaps in it, because that way you have a lot of heat loss. They are expensive, but they're very durable, and they are very good for foundations and marine applications, and also solar collectors. They're expensive, but they last for a long time, and especially if you have foundation, you cannot imagine how much heat loss you'll have through the foundation, because it's completely solid and it's concrete and it has steel in it, so you're gonna lose a lot of heat through that. Marine application, if you have houses that built close to the shore, they are water resistant. So there are some cement that is salt resistant that can be built in the water. So you see that all the time, it's gonna be in the water and just drying off. Also used for solar collector, because again, we're looking for durability and water resistance. Blown fiberglass and mineral walls. Mineral wool is very expensive and it's very durable and good material. But again, cost is always a factor. People do not like to put a lot of money, even though it is useful and it's a good investment. But you see a lot of thousands being used for insulation, and people are, okay, I'll deal with that later. People will usually look at the capital investment, they don't look at the return on investment and how long will that cost you over time. So, blown fiberglass is another option. And as Connor said, once you do the blowing, you have to cover it up. You can't just leave it loose, otherwise it will collect dust. It will become airborne, and it's not good for your health. They're made of very low bats with lower R value, and than bats. Why do you think they have lower R value than bats? Density. It has different density and it's more porous. So even though it's the same material, the packing factor and the layers make the bats a better option than blown fiberglass. They are sold in bales, like you get them in like big bags, and you can just load them in. They require a blowing machine with an agitator to keep it fluffed. And again, we said there's a relationship between density and R value. So you have to have the right R value and the right density, otherwise it's not going to be your insulation. There are always issues with machines, so you have to bring the machine to that place. It's like a big huge vacuum, you have one in the back where you bring a truck full of blowing insulation and you pump that up. It's always an issue. It's not like a vacuum that also acts as an agitator. So if it does not spread the blowing insulation evenly, you don't get the right value. Plumbing leads to extra air permeability, and you don't want that, because again, we said airflow is always work against insulation. Fiberglass should be at least 0.7 pounds per foot cube in density. That's for fiberglass. If you look in your book, there are a lot of values and a lot of good tips about current insulation. And pay attention to those details. Now you understand what density means. You understand K value a little bit. R value, U factor. So when you go and look at those numbers, they make sense to you. Like, I'll put in a whole board to give you the information. So you'll see thickness, R value, reflective surface R value, and they tell you also that the airspace, the vertical airspace between, that should be left between each panel. Otherwise, not going to be effective. So whenever you do any blown-in installation, you're going to expect settling. Again, you go in, you settle, you go again and measure the depth, measure the density, and you see how much you put in there. And probably before they go and blow the insulation in, they will tell you you're going to need, for example, 50 pounds of insulation or 40 pounds of insulation. So they'll go, they blow it in to settle, and they keep packing it until you reach the right weight. So you buy it by weight, you put it by weight, and a lot of businesses actually, they make money, they try to jip you on the amount of insulation. It looks like it's done, but it's not. And again, it's labor intensive, there's a lot of labor charge in it, and also the material. So make sure that you understand what's going on. Yeah, I'm blowing insulation. How are you selling me the insulation? By what R value and by what density? So that's something you have to think about. And probably they don't know. They at least eyeball it.
Then the technician probably.
Yeah. So somebody should tell you that, and probably that's something from you now. So you understand now how it works. Question?
I went over to rent one the other day, to do my attic, and the guys that were in there just grabbing the bales to do it.
Yeah. So, granted, not everybody knows what's going on, but I'm explaining to you now how it's done and how you properly can get it working correctly. Otherwise, you're just putting some dirt in your basement, on your attic. Just blowing some garbage over and it's not like doing insulation if it's not packed correctly. If you pay the money, you want to make it work correctly. And again, we said where do you lose most of the heat? From the attic. So that's the best place you want to insulate, and you should invest some good money in it.
It's like what, 3 feet per square foot, right?
Say what?
Blown insulation, 3 feet per square foot.
It depends on the material, and it should say on it what R value I'm getting. And how do I know if this insulation is good? Is when you do your heat loss analysis. You see the type of ceiling you have, and you'll figure out that this is not really good ceiling. So you add some insulation, and you recalculate until you're satisfied it's not good insulation.
If I have,
Yeah.
is it mandatory to properly insulate just the garage?
I think for new houses, depending on the town, some places you don't have to, but in some town you have to insulate before you get like a permit. Yeah. Do you have any questions? Any feedback? Any addition to? Yeah, go ahead. Huh? Yeah, we'll do more. Next on Friday, remind me. I'll do a couple of more.
It's gonna be in the quiz.
Huh? Yeah. Quiz is only 20 minutes. Okay.
Wait, did you go